is Julia Van Langen. I am a math and computer science major at Otterbein University, and today I'll be talking about my honors thesis project on the Mersenne prime numbers. So a little bit of history about number theory in general. It is one of the oldest fields of mathematics, dating back to Pythagoras' school of thought in 550 BC. One of the oldest and most well-known theorems in mathematics is the Pythagorean theorem. We all know and love it from high school. Number theory also houses some of the most famous open problems in mathematics. This includes the Riemann hypothesis, the Goldbach conjecture, and the twin primes conjecture. Unfortunately, we will not have time to go over these in depth today, but I encourage you to go to look them. They're really interesting. Number theory also has numerous applications in almost every single subfield of mathematics, and in many, numerous other fields as well, including cryptography, which is another field of interest for me. So a little bit about our topic for today. In 1644, Mersenne made a very bold claim, stating that the number 2 to the n minus 1 is prime for n equals 2, 3, 5, 7, 13, 17, 19, 31, 67, 127, and 557, and that it was not prime for any other n less than 257. Ultimately, this claim was false, but it took almost 300 years for the correct list to be determined, and that's 2, 3, 5, 7, 13, 17, 19, 31, 61, 89, 107, and 127. So you notice those lists are actually very close, and this is very impressive because in the 1640s they didn't have any electronic computation devices to help with those computations. So it's very impressive that Mersenne was that close on his calculations. Due to his work with this type of number and prime, they were dubbed the Mersenne numbers and primes respectively. So these two definitions are really important for us. We say that a number mn is a Mersenne number if it's of the form 2 to the n minus 1, where n is a natural number. And a prime number, mp, is called a Mersenne prime if it is of the form 2 to the p minus 1 with p prime and p greater than or equal to 2. So these are the kind of numbers we're going to be talking about today. A little bit about prime numbers in general before we jump into the Mersenne primes. A prime number is a natural number, p, that is strictly greater than 1, that's divisible only by itself and 1. Prime numbers are the building blocks of all of mathematics, and this is evidenced in our fundamental theorem of arithmetic. This theorem states that every integer greater than 1 can be uniquely factored into a product of primes. Now, we all have actually used this theorem, and we're taught it from even in elementary school, but we weren't told that it was a theorem, and we weren't told about its proof because it's actually quite complicated, and it uses the result of another theorem. In about 300 BC, Euclid proved that there are an infinite amount of prime numbers. Unfortunately, due to time constraints, we can't talk through Euclid's proof, but I encourage you to look it up. It is one of my personal favorite proofs. It's very elegant and beautiful. So we know there are an infinite number of prime numbers, but what about Mersenne primes? Unfortunately, we currently don't have any answer to that question, but there's been quite a bit of progress recently. In December of 2018, the 51st Mersenne prime was discovered. We also know a very clear structure and relationship between the Mersenne primes and another set of numbers called the perfect numbers. We'll talk about that later. And there's been major advances in primality testing recently due to the Lucas-Lehmer test. Due to the Lucas-Lehmer test, all of the most recently found largest prime numbers are actually Mersenne primes as well. Each of these things brings us a little bit closer to finding the answer about if there are an infinite number of Mersenne primes or not. So, one of the first efficient primality tests for numbers of reasonably small size was for Ma's little theorem. It's called a little theorem, but it's actually really important. It is not only was it one of the first primality tests, but it's used in the proofs of numerous other theorems. And it's also worth noting that the lemma used to prove for Ma's little theorem was also used in the proofs of numerous other theorems as well. So for Ma's little theorem tells us that if p is a prime number, and a is any number that's not divisible by p, then a to the p is congruent to a mod p, or equivalently, a to the p minus 1 is congruent to 1 mod p. So note that you will see it show up in both of those forms in different contexts, but just remember that they are equivalent. So before we dive into a couple more theorems, we need to define some things first. The first thing we're going to define is that a non-zero number that is congruent to a square modulo p is called a quadratic residue modulo p. On the flip side of that, a non-zero number that is not congruent to a square modulo p is called a quadratic non-residue modulo p. Now, those are very abstract kind of definitions, so we have the Legendre symbol that we are going to use to give us a more concrete way of looking at these things. The Legendre symbol of a modulo p is denoted like this, and we say that it's equal to 1 if a is a quadratic residue mod p, and negative 1 if a is a non-residue mod p. So this just lets us assign a numerical value to, so that we can use it in calculations about if the Legendre symbol is, if a mod p is a quadratic residue or a non-residue mod p. So before we move on to the next topic, I want to kind of give us a roadmap of where we're going. Unfortunately, we won't have time to look at all of the theorems that are involved in the next couple theorems, but it's really important to note that while these theorems might not look like they're related to our topic right now, it's like they're all a piece of a puzzle. So on the surface, it doesn't look like they're related, but they will all string together to come and let us prove something that's a lot more powerful. Unfortunately, we won't have time to see how they all fit together, but I encourage you to go look at my paper. It's laid out there. It's really pretty. So the first of these theorems that we're going to talk about is Euler's criterion. Euler's criterion lets us relate the Legendre symbol of a number to a more easily calculated quantity. So Euler's criterion tells us that if p is an odd prime, then a to the p minus 1 over 2 is congruent to a mod p, is the Legendre symbol of a mod p, where a is just any integer. Now, like Euler, Gauss proved another theorem that relates the Legendre symbol of a modulo p to a more concrete quantity. However, the quantity he relates it to is a slightly more complicated, so we're going to talk about it first. So we say that mu of AP is the number of integers in the list a times 2a, 2a, 3a, all the way up to p minus 1 over 2a, that turn negative when they reduce modulo p into the range from negative p minus 1 over 2 to p minus 1 over 2. So what does that mean? That means instead of reducing these numbers from 0 to p minus 1 like we normally would, we're going to shift everything over. And now they'll be from negative p minus 1 over 2 to p minus 1 over 2. So that means roughly half of this list are going to be negative when we reduce them into this special range. And mu is the value of the number of those integers that turn negative when we reduce them. So Gauss's criterion tells us that if p is an odd prime and a is an integer that's not divisible by p, then the Legendre symbol of a mod p is equal to negative 1 to the mu a p. So as you can see, those the Euler and Gauss's criterion can very simply be strung together to give us two quantities that we can calculate easily that have to be equal to each other. The next thing we're going to talk about is the law of quadratic reciprocity. And the law of quadratic reciprocity clearly has three parts to it, and each of these parts serve a unique purpose. The first part lets us determine what the Legendre symbol of negative 1 mod p is. The second part will let us determine the Legendre symbol of 2 mod p. And the third part will let us determine the Legendre symbol of any p and q distinct odd primes of what a q mod p is going to be. So at this point you might be kind of asking, okay, what's the big deal? We've led up to this law of quadratic reciprocity. Why do I really care? Well, the law of quadratic reciprocity is actually one of the most powerful theorems in number theory. It lets us determine the Legendre symbol of any prime q mod p incredibly easily. And while that may not seem important on the surface, there's many theorems for which this is very important in their proofs. One of these such theorems is the Lucas-Lambert test, which we're going to talk about next. So the Lucas-Lambert test is our test for primality of Mersenne numbers. And this is how the Mersenne numbers are determined if they're prime almost always nowadays. The Lucas-Lambert test relies on this recurrence relation. And this recurrence relation says that Si is equal to 4 if I equals 0, and otherwise it's equal to Si minus 1 squared minus 2. So the first couple examples of that, S1 is going to be S0 squared minus 2, or 4 squared minus 2, which is equal to 14. S sub 2 is 14 squared minus 2, which is 194. And S3 is 194 squared minus 2, which is 37,634. So as you can see, the numbers get very large very quickly, which is why for the rest of our calculations, our examples, we're going to keep those exponents pretty small. So here's the actual test. This is the reason why we can use this test for determining the primality of Mersenne numbers. Lucas and Lambert proved this and said that MP is prime if and only if S sub p minus 2 is congruent to 0 mod MP for p strictly greater than 2. So notice that this is an if and only if statement. This means that if we have either one of these conditions, the other one follows immediately. Basically, these two conditions are exactly equivalent. So a couple of examples of how this works. Let's say that p equals 3. Then MP is 2 to the third minus 1, which is 7. For the sake of our example, let's pretend that we don't know if 7 is prime or not. Well, S sub p minus 2 is S sub 1, and that's 14 by our previous calculations. And 14 is congruent to 0 mod 7. So great, 7 is prime. But we already knew that. But now let's say that p equals 4. Then MP is 2 to the 4 minus 1, which is 15. Again, pretend we don't know if this is prime or not. And S sub p minus 2 is S sub 2, which is 194 by 4. And that's congruent to 14 mod 15. So 15 is not prime. But it's also important to note that we already knew the second example would not be prime because we know if the exponent is prime, the exponent is not prime. We can always find a factor and the result will never be prime. So the last topic I want to talk about today is another set of numbers that is called the perfect numbers. These are the numbers for which their proper divisors sum to themselves. For example, the first two perfect numbers are 6. 6 is divisible by 1, 2, and 3. Notice that we do not include 6 itself because it's only the proper divisors. And 1 plus 2 plus 3 is equal to 6. Likewise, 28 is divisible by 1, 2, 4, 7, and 14, and 1 plus 2 plus 4 plus 7 plus 14 is equal to 28. And the same holds for 496 there. So at first glance, it may not look like these perfect numbers and the Mersenne primes are really related at all. However, in early 18th century, Euler proved two theorems that together create a very powerful statement and a very close relationship that we can see between the Mersenne primes and the perfect numbers. The first of these states that if n is an even perfect number, then it has a form 2 to the p minus 1 times 2 to the p minus 1, where 2 to the p minus 1 is a Mersenne prime. So for every even perfect number that we have, we can find a Mersenne prime. On the flip side of that, if 2 to the p minus 1 is a prime number, thus a Mersenne prime, then 2 to the p minus 1 times 2 to the p minus 1 is a perfect number. So for every Mersenne prime that we have, we can find a perfect number. So this is really important because if we were to discover that there were an infinite number of perfect numbers, we would automatically have that there were an infinite number of Mersenne primes. And if we were to discover that there were an infinite number of Mersenne primes, we would also automatically have that there are an infinite number of perfect numbers. So while on the surface it may not seem like these are related at all, they're incredibly closely related. So in conclusion, while we do know quite a bit about the Mersenne primes and prime numbers in general, there's still a lot we can learn. We talked a little bit earlier about the Riemann hypothesis. This is thought to be related to the distribution of prime numbers. In fall of 2018, Michael Atiyah claimed to have proven this 100-year-old hypothesis. However, his proof is widely not accepted in the mathematical community. Another such open problem is the twin primes conjecture. This is the conjecture saying that there are an infinite number of twin primes, and these twin primes are primes that differ by 2, for instance, 17 and 19. Also, for hundreds and hundreds of years, since the ancient Greeks, we have been searching for an odd perfect number. Currently, all of the perfect numbers that we know of are even, and it hasn't yet to be shown whether there is an odd perfect number or not. And of course, we still do not know if there are an infinite number of Mersenne primes, as we've been talking about today. I want to say a huge thank you to all of my family and friends for their support over the past 2 years in this project, to my entire honors committee for taking time out of their busy schedule in this crazy time, and specifically to my advisor, Dr. Jeremy Moore, for helping me through the past 2 years on this project. Feel free to reach out with any questions you have. Thank you.